Good morning, Chemistry 20s. Our lesson today is on concentration of ions. So, as we have discussed in previous videos, many substances when placed in water are going to dissociate or going to ionize into solutions. What I would like to do today is let's write an ionization or dissociation equation. So, NaCl, we know will dissociate. Again, if you'd like to check your solubility table, please do. It's highly soluble. So, NaCl, when I drop it into a bucket of water, is going to break into Na positive ions and Cl minus ions. Now, we always balance atoms first. So, one sodium on the left, one sodium on the right, one chlorine on the left, one chlorine on the right. Now, however, though, we always secondly balance charges. So we have no charge on the left-hand side. It's neutral. One positive plus one negative, no charge on the right-hand side. This dissociation equation is complete. Let's do the second one together. Lithium phosphate. Again, we're going to go to our solubility table. We're going to look up lithium phosphate because it's ionic. Under phosphate, lithium's group 1, so it's going to be highly soluble. So this guy's going to dissociate into Li positive aqueous and PO4 minus aqueous. So three lithiums on the left, one on the right. So we're going to need a 3 here. One phosphate, one phosphate. 3 minus plus 3 positive, no charge on the right, no charge on the left. So this is balanced as well. For each of the following substances, write the dissociation equation if possible. I say if possible because if our substance does not dissociate, meaning if it's a weak acid, if it has a low solubility when it comes to ionic or a base, it will not dissociate. Can you take a second and try these two for yourself, then unpause the video to check your work? So I look up calcium chloride. Calcium chloride is highly soluble. Therefore, it's going to dissociate into Ca2 positive ions and chlorine ions. So we have one Ca, two Cls. I'm going to need two Cls. 2 minus plus 2 positive, no charge on the right, no charge on the left. I want to add in at this moment that we do not add water to this. Although we're putting these into water to make a solution, I don't have to add water on the left or water on the right for a dissociation equation because water is already represented by us putting aqueous on the ions. Because remember, aqueous means dissolved in water. So let's try the last one, silver sulfate. When I check this example in my solubility table, you will notice that this has low solubility. Therefore, I cannot write a dissociation equation because it does not dissociate. And again, if you get one of these on a worksheet or on a quiz or test and it doesn't dissociate, all you have to do is tell me, does it dissociate? And therefore, you can't do the question. What I want you to notice is from the 3 examples we've done, this one on this page and the 2 on the previous page, the ion concentrations are always written in whole number coefficients. This is important for the next step that we do. Remember, every time we're balancing, we're using these whole numbers to make sure that everything is equal on the left and on the right. So the dissociation or ionization equations for soluble ionic compounds, this would include, of course, bases, or strong acids, allow us to determine the amount concentration of either the ions or the compound in the solution. So we can use the concentration of one of those to find the concentration of another. To do this, we're going to have to do 2 steps. One, write a balanced dissociation equation. Again, I only do that if it's highly soluble or a strong acid. And then 2, I can do a concentration statement. So let's see what this is going to look like on the next example. Here's my example, example 1. What is the concentration of hydrogen ion and the chloride ion in a 1.50 moles per liter hydrochloric acid solution. So my substance is HCl. I know by looking on the chart for acids that hydrochloric acid is a strong acid, therefore it will dissociate. So I'm going to write HCl aqueous. And again, when it dissociates or ionizes, it breaks into hydrogen ions and chloride ions. Now, the one thing I like to do when we're actually in class doing this is I like to use a red pen for this because it tells me the concentration of HCl. And so that concentration is 1.50 moles per liter. And I'm going to go back then. But I always do it this way because it allows us a chance for it to stand out. And that standing out part is really important for us, and we'll see why here in a second. So what I would like to do is, what we said was, if we know the concentration of one substance, and it can be any of these three substances, if we know the concentration of one, we can find the concentration of any or all the rest of these substances, like these two ions. So I would like to find the concentration of hydrogen ions first. Now, in chemistry, when I use a set of square brackets, this means concentration of. So I am trying to find the concentration of hydrogen ions. Here's what we're going to do. Take the concentration you already know, the one that you've written in red. So 1.50 moles per liter. And remember, that's the concentration of HCl. So also write down the substances. And we're going to play a little game of leapfrog. Since we're trying to find the concentration of hydrogen ion, we've written down the concentration we know, and we're going to do a little game of leapfrog, and we're going to multiply by the coefficient of the hydrogen ion. So times 1 mole of H positive. And in this little game of leapfrog, we multiply by 1 mole of H positive, and then we're going to leapfrog back. And we're going to jump back, and we're going to divide by 1 mole of HCl. The order of this is really important because remember, as we set this up, my end goal is to get the concentration of H positive. Therefore, I want to get rid of the HCl's. So if I have the HCl concentration I know on top and the moles of HCl on the bottom, the HCl's will cancel out. I can also cancel out moles on the top, moles on the bottom. So I'm going to take my calculator and I'm going to go 1.50 times 1 divided by 1. So my answer mathematically is going to stay exactly the same. Notice the only unit I have left is moles per liter. And the substance we're solving this for is, along the top, H positive. So from the beginning, we have been trying to find what is the concentration of H positive. We know the concentration is 1.50 moles per liter H positive. Hydrogen ion is 1.50 moles per liter. Let's do the same thing, but this time let's write a concentration statement for chloride ions. So again, take the concentration you know, 1.50 moles per liter. Now we are going to, and this is for HCl, so we got to write down what it's for. We are going to play again a little game of leapfrog. So we took this concentration times by 1 mole of Cl minus. And then we're going to leapfrog back, divide by 1 mole of HCl. Well, moles on top, moles on bottom, they're going to go away. HCl on top, HCl on bottom, they're going to go away. And I'm going to be left with 1.50 times 1 divided by 1. So that's going to be 1.50 again. My only unit left is moles per liter. And the substance I'm left with is chloride ions. So our job was to find the concentration of Cl minus. Our concentration is 1.5 moles per liter of Cl minus. Now, it's at this stage where it tends to be that people get a little bit confused. And they get confused because they get a little lost in the idea of concentration. And they go, how can I have 1.50 moles per liter of HCl and it splits into two substances Shouldn't my concentration split into two things? Like, shouldn't we divide it by two? How are both of these numbers exactly the same? Well, I want you to think of this as iced tea. Hey, I have a container of iced tea. Well, if I take my iced tea and I pour it into two glasses, my concentration of the iced tea doesn't change. If I take a drink out of glass one, or I take a drink out of glass two, or I took a drink out of the jug before we started, all of the concentrations of this iced tea is exactly the same. When you think about the idea of, hey, I have 1.5 moles per liter of HCl, when I split it, shouldn't it split into like 0.75, 0.75? You're not thinking concentration. You are thinking volume. You're thinking, hey, if I have a container of iced tea and I split the volume in two, I'm going to have half as much in each. That is correct, but we're talking concentration. So I would like us to probably think of it this way. So I take HCl and I drop it into a beaker of water, right? When it dissociates into its ions, I have the same concentration of H positive ions than I do of chloride ions. It's a 1-to-1 relationship. Whether I'm talking the big jug of iced tea or glasses of iced tea, the concentrations of these ions do not change. Now, the last thing we should talk about when we go to do this is how many marks is this worth? You would get 1 mark for the dissociation equation. You would get 1 mark for showing me the concentration statement, and that's what this is. If you just give me the answer, I will give you no marks. I need to see your work. I need to see the concentration statement. And you would get another mark for the second concentration statement. Okay, at this stage, what I'm going to do is I'm going to pause. You can then go and watch part 2 of this video where we're going to do another question like example 1, and then we're going to do a little bit harder question. We're going to build up to see how this can be more realistic in the lab.